The next chapter is magnetic fields. So first of all, let's see all the type of forces and fields. First, there are three types we see normally, which is first is gravitational force, and one is electrostatic force, electrostatic force, or we can call it electric force, and the third one we will study here is magnetic force. For gravitational force to occur, there is need of two mass. For electrostatic force to occur, there is need of two charge, and for magnetic force to occur, there is need of two charged particles moving with some velocities v1, v2. So there is need of some moving charge. We can call it moving charge, and the force depends on the velocity and the magnitude of charge also. In case of gravitation, the let's say there is a mass m1 here, 8.1, and 8.2 there is mass m2 here. Then the gravitational field due to this mass m1 at this point 2 would be written as g gravitational field at point 2 due to 1 mass at 1 is given by g gravitational constant into mass m1 into the vector r21 cap divided by r21 square. In case of electrostatic force, this electric field at this 2 point due to this charge q1 is given by electric field at 2 due to the 1 is equal to the constant k multiplied by q1 r21 cap divided by m1 sorry r21 square. And in case of magnetic field, the first of all, this g value, this g constant is equal to 166.67 into 10 to the power minus 11, and this g value is independent of medium. So this value is taken independent of medium. If there is a mass m here and there is a mass m here placed m2 and there is mass m1 here and there is mass m3 here, then the force on then the field gravitational field at this point due to this mass is unaffected by this mass. So the field at this point would be equal due to the mass 2 and due to this m1 mass. So we have to take the sum of gravitational fields due to both masses. And in case of electric field, this k is dependent on it depends on permittivity. It depends on permittivity of space. Permittivity means the opposition provided to the electric field. Permittivity is a property of medium. Whenever there is some electric field we apply to the medium, it tries to oppose the electric field because whenever there is a medium, let's say it has some atom in the medium, there is any atom in the medium, then what happens, this negative charge moves in this direction and positive charge moves in this direction, producing some positive charge in this direction and negative charge in this direction. Now this produced charge will produce electric field in this direction. So the electric field produces a new electric field E produces in the matter. This is the electric field due to the matter. So the electric field when present in the matter, then the matter also produces some electric field which opposes this electric field. So the matter electric field opposes this electric field which affects the total electric field at any location, and that is what we call that factor by which the electric field is affected, we call it permittivity. And permittivity is denoted by this epsilon sign, where k is equal to 1 upon 4 pi epsilon. This is the value of constant. When there is vacuum, when the vacuum medium is used, then this value of k is equal to 1 upon 4 pi epsilon naught, which is equal to 9 into 10 to the power 9. It depends on the medium. K depends on medium. And the force in this case on the mass 2, if there is gravitational field due to mass 1 at this point g21, then the force on this mass m2 due to this gravitational field will be equal to force on the mass m2 would be equal to force on mass m2 would be equal to g21 vector multiplied by the mass of 2. And in this case of electric field, let's say this is called gravitational force. And in case of electric field, there is some electric force applied on this charge q2 due to the field of q1 at this point, which is given by the field u21 at this point multiplied by the charge q2 on which we are talking about, on which we want to calculate the force acting. Now, in case of magnetic force, first of all, we will find the magnetic field B at any point. Let's say this is the point 2 and this is, let's say there is a charge q1 here at point 1 moving in any direction v1 with v1 velocity in any direction. There is charge q2 at point 2. This is moving, let's say, in any direction with v2 velocity. Then in that case, the magnetic field due to this q1 charge at this 2 point would be equal to b at 2 due to the 1 is equal to some constant value k multiplied by the q1 into v velocity of the charge 1 cross r21 cape divided by r21 square. So this square of distances comes in all these three equations. And in case of magnetic field, there is a need of velocity also, and this is the position vector of 2 with rest from this one point. And the magnetic force at the point on the charge 2 would be given by F magnetic force is equal to, due to this magnetic field V21 would be Q2 into V2 cross B21. B21 is the magnetic field at the point 2 due to this one. So this is the force on Q2 due to Q1. This is the force on Q2 due to Q1. Similarly here, this is the force on M2 due to M1. So in case of magnetic field, we have to take care of the velocity, and the force is given by the direction of magnetic field here at this point would be, since velocity is in that direction and r is in this direction, so v cross r will give the magnetic field at this point in inward direction, going inward this plane. And the magnetic force Fp acting at this charged particle would be v2 is in the direction and magnetic field is in the downward direction, so v2 cross b will give a force in this direction. So F B on this charge q2 would be acting on this direction. And we can apply action reaction law also in these cases. Let's say there is some FB force, F force acting on this 2 mass, then the same force would be acting on this M1 mass in the opposite direction due to this. Similarly, if there is a force F acting on this Q2 charge due to this Q1, then there would be some force acting on this Q1 charge due to this Q2 in the opposite direction. This is called action reaction law. In this case, we can also calculate V2 is in this direction and R vector is in this direction, so V2 cross R gives the magnetic field in the opposite direction represented by a dot, and v1 cross this magnetic field will give a force in this direction F. So if there is a force acting on this direction on this q2, then there would be some force acting on this q1 charge in this direction. Is it right or not? q2 is moving in this direction, v2 we get v2 cross this is v2, and this is cross this angle is what the cross will still be. The cross is taken along this smaller angle. This is the smaller angle, so we will take the cross in this way, not in this way. So the v2 cross r is taken in this way, and the magnetic field is upward. So v cross r will give the force in this direction, and on this the field is this way downward, and v2 cross this will get. So in this case of magnetic force, the force doesn't look like to be acting in the opposite direction, because this is acting in this direction while this force on this charge is not acting in this direction. So action reaction law in this case of magnetic force. So in the case of magnetic force, the Newton's third law of action reaction pair is not obeyed. Not necessarily, not necessary to be obeyed always. Sometimes it can obey. Let's say these two particles are moving in the same direction, then there would be attractive force like this. Then both are in the opposite direction, both forces are in the opposite direction, then we can say it is obeyed. But in this case, the forces are not in the opposite direction, so in this case the Newton's third law is not obeyed. So magnetic force does not always follow the Newton's third law, but these two forces follow the Newton's third law. So third law here works in these two cases, but not in this case. And the magnetic force for this chapter, these two formulas are very important for us. We should keep in mind. Now, deriving the Biot-Savart's law from this equation. Biot-Savart's law is an outcome of this relation. Let's say there is a charge flowing in a arbitrary path. Let's say I current is flowing in a arbitrary path, and I take a very small element of this path. Let's say dl, and I treat this dl as dl vector, where the direction of this dl vector is same as the current. So if the current is flowing in this direction, so the dl vector will also point in this direction. And let's say there is a point P in the space here. This whole length is so small. This is so small that I can treat it as a point charge. This can be treated as a this dl length can be treated as a point, and the total charge, let's say it contains dq charge which is moving. Let's say it contains dq charge which is moving, then I can assume it to be like a dq charge located at this point, and I want to find the field due to this dq charge at this point, and I can use this formula now. And here in this case, let's say the dq charge in this takes dt time to come out of this length dl. Let's say the charge at this end takes dt time to come out of this other end, then it means the total charge took dt time to come out of this, to flow out of this point, this cross section. The current is equal to the dq charge which passed out divided by the dt time, and the length which it traveled is dl, and dividing it by the dt time will give the velocity of this charge. So now I know the velocity of this dq charge, which is in the direction of dl cape. Now I can write this formula, and here this value of k, when there is vacuum, then this value of k is 10 to the power minus n, But when there is a medium used, then the value of k is replaced with 10 to the power minus 7 times mu relative. That is a relative permeability. The formula of k is equal to mu upon 4 pi, which is written as mu relative into mu naught divided by 4 pi, where this value of mu naught upon 4 pi is given as 10 to power minus 7, and multiplying it by mu r is equal to this k value. And if vacuum is used, then mu r becomes 1. Mu r is equal to 1 for vacuum. Now in this case, for calculating the field at this point P, let's say this vector is r cap and the length is r, then the field at this point P would be equal to, magnetic field at this point P would be equal to k times this dq charge bracket the velocity of this charge, which is dl by dt in the direction of dl cap. This becomes dl vector by dt multiplied by the distance vector, which is this r cap unit vector of this, and r square. Now this gives the magnetic field at point P, and now I can write dq is equal to I dt. So this gives I dt cancels dt, we get dl cross r cap divided by r square, the magnetic field at point P. And this form of equation of magnetic field, this is called Bayer-Savart's law. This is derived from this equation. This equation gives this. So the main equation is only these two. That force is given by Q into V cross P, and magnetic field is given by K into Q V cross R cap. Order of these values V and R and V and V is important in case of cross product. Otherwise the direction of the force or magnetic field will get changed. And there is a simple way of conversion, since in case of writing this, let's say there is some charge there is some charge q flowing with some velocity v, then it can be written as I dl. Let's say some dq charge is flowing with some velocity v, then this can be written as I into dl. And this dq can be written as I dt, and v dt will give that length v dt. dq will be equal to I dt, and v dt will become dl. This gives I dl. So we can use this conversion for simply converting from this form of equation to the Bayer-Savart's law. When there is current given, then we will use this. When there is point charge given and velocity given, then we will use this formula. Both are same formulas, just little bit modified. And now in case of, now there is one more term called Lorentz force. Lorentz force is simply the force due to the electric field and plus the force due to the magnetic field on any charged particle. Let's say there is a charged particle q here, q naught, and there is any electric field at this point, some magnetic field at this point, and this charged particle is moving with some velocity v naught. Then there would be some magnetic force on this particle Fp and some electric force due to the electric field Fe. Then this sum of this electric force and magnetic force, this is called Lorentz force. This can be given by q bracket electric field. This gives the electric force plus v cross b, which comes from this relation. This gives the magnetic force. So electric force plus magnetic force. Now there is another term we have called flux. Just like in case of electric flux, we have magnetic flux, which is given by simply the small flux is given by, let's say, the number of field lines passing The number of field lines, the flux concept can be understood as the number of field lines passing through an area. Field lines passing through an area in one direction. Let's say there is some field lines passing in this direction and some field lines passing in this direction. Then we will say this is negative. This is, let's say, this direction of passing, this direction is taken as positive, then this will be negative. So this will give a negative flux and this will give a positive flux. So we will overall get only two field lines passing through this area as net. So flux is more correctly said as the number of field lines passing through an area in a direction, and it can be given by B dot dA. And if the magnetic field is in this direction and the area vector is taken in this direction, then this product, the dot product of them would be this d phi b. And the direction of this area vector, when there is open surface, let's say there is a open surface here, there is a small d element here, then in that case, if the electric field is passing in this direction, then area vector is taken in this direction. And if electric field is magnetic field is in this direction, then area vector is taken in this direction, and the direction is perpendicular to the surface. But if we take a closed surface, then by convention we take the area vector outside the surface. So even if the magnetic field is inside, we take the area vector outside. Doesn't matter the magnetic field is inside or outside, we will take the area vector outside in case of closed body. And there is one Gauss law for magnetic field. This is called, this next term is Gauss law for magnetic field. Before telling this, we have to understand one thing, that the magnetic field lines always come in loops. Let's say there is a charged particle Q here moving with some velocity v in this direction. Then there would be some magnetic field around this charged particle in a circle. A magnetic field is produced in circle. In this circle, around this point C, around this point charge, will have equal magnitude in this circle, and the direction of magnetic field would be like this. And the magnetic fields always occur in loop. This is the important point here. We noted that magnetic fields always occur in loop. In case of electric field, the electric fields do not occur in loop. They do not occur in loop, but in case of magnetic field, it always occurs in loop. So it means if I take a closed surface, that is Gaussian surface, if I take a Gaussian surface here, and there is any magnetic field going inside this surface, then it should also come out this surface, because it has to complete a loop. If it doesn't come out of this Gaussian surface, this loop will not complete. So to make sure that any field line is going inside, and to complete this loop, this field line must come out of this surface. So if this field line going inside and also coming outside, the number of field lines going inside is equal to the number of field lines going outside. So the total flux phi net all over this surface would be equal to 0. We can say that the summation of all B dot dA, if I say the summation of all of the P dot d over the surface, all over surface of this Gaussian surface, closed surface, this will give 0 here. In case of closed surface or closed surface, and there is another law in case of magnetic field, that is called Ampere's circuital law, and that is given by, that is about, let's say there is a loop here, any shape of loop, and this is a line, and let's say I am taking the integration of b dot dl over this whole loop, over this closed loop. I am taking a integral of p dot dl. Let's say b at any point is in this direction, and I am taking the dl vector in this clockwise manner. So dl vector is pointing in this direction, and magnetic field is pointing in this direction. Let's say magnetic field is pointing in this direction, then I have to take the dot product of this p dot dl and integrate it all over this line segment, and this whole integral will be equal to mu times I of active, where mu is equal to the permeability of the medium here. Let's say this medium has some permeability. This medium in this region has some permeability, let's say mu, and the total current passing through this loop, this is equal to, let's say, I effective. Then then this I effective is equal to this whole integral of p dot dl divided by the mu value, mu, where this I effective is equal to the current due to the flow of charge. Let's say that charges are flowing this due to the current, and there would be some current due to the displacement current. Displacement current is due to the electric field, so this is due to the electric field, and this is due to the charge flowing. This is the corrected formula of Ampere circuital law, where I effective is given by IC plus I displacement. And let's say I have taken the current in this clockwise manner. Sorry, if I have taken the dl vectors in this clockwise manner, and this whole value becomes positive, this whole value is, let's say, positive, then in that case I will say that magnetic field might be in this direction, and I will take the current in this clockwise manner. I will rotate my hands, curl my fingers in the clockwise manner, and when the direction in which my thumb points, that would be the direction of I effective. So if I take this dl vector in this anti-clockwise manner, so I will have to take the direction as in this direction, let's say anti-clockwise manner. It means the I effective should be in this upward direction. If this value turns out to be positive, then the current would be upward, I effective would be upward, and if this value becomes negative, then it would be in the downward direction inside this loop. And that is Ampere circuital law. Now moving ahead, we have some formulas for magnetic field due to system of charges moving. This was due to the magnetic field due to the point charge moving, and let's say there is a straight wire. This is a straight wire with some, let's say there is a point here in the space P, and this is a straight wire carrying some current I in this direction, let's say. Then this and this A, and this is B. This is a finite length of current carrying wire, and let's draw a perpendicular line from this length to this point P. Let this perpendicular length from this line is R, and similarly, just like we did in case of electric field, we will draw an angle here theta1 and angle here theta2, and one angle is taken positive in this direction and one angle is taken positive in this direction, just like in case of electric field. And there would be the total electromagnetic field at this point, let's say B net. This can be given as First of all, the direction of this magnetic field would be given as right hand rule. I thumb points in the direction of current, then this curl of finger tells the direction of magnetic field, which is upward. So the magnetic field is here is upward, or I can say the direction of charge is in this direction, velocity is in the direction, and the r is in this direction. So v cross r, this gives the velocity magnetic field in this upward direction. And the formula of magnetic field at this position B is equal to simply K times I divided by this length R, bracket sine theta 1 plus sine theta 2. And if this point P lies at this point, let's say here, then this theta angle will be, let's say, parallel to this. This theta angle would be equal to this angle theta, and this is, let's say, taken as positive. This length is, let's say, R, and this angle would become theta 2, and this angle would be taken as negative. Let's say the magnitude of this angle is phi, then theta 2 would be taken as minus phi, because one angle is taken positive in this direction, then other would be taken negative. So this is how we will calculate the magnetic field due to the finite length of wire. In case of electric field, we had two formulae of magnetic field here. One was in this direction and one was in this direction. While in case of magnetic field, the magnetic field is in this direction or in this direction only, and its formula is single, this one. And now the other case of magnetic field, let's say there is a arc of, let's say, a radius. It has a radius r, and this is the center point of this arc, and a current I is flowing in this circuit in this arc from A to B. This is arc A to B, and let's say this angle is alpha, and there is a axis passing through this center point, which is perpendicular to this plane of circle. Let's say this is a circle, and there is, I draw an axis of the circle, this one, and any point on this axis, let's say P, draw the line joining this point P and this arc, then the angle between these two lines, let's say it is beta, just like in case of electric field we did. We will do here again, and in this case this I is in this direction and R vector is in this direction, so the I cross V will give B net in this direction. The magnetic field due to this small part is in this direction, and if I take the integration of all paths, the magnetic field from this to this all will give a net direction in this, which is the direction of B net is parallel to this axis, parallel to this line passing through this point. This is the line which cuts this arc in two equal parts, means this line about which this arc is symmetrical. Let's say this line is let's say this line is L, then we have to take a line parallel to this line, then the B net will occur in the line in the plane which is in this line and this line. Now this B net can be written as its two components. One is in this direction, which is called B perpendicular, and one in this direction, which is called B parallel. This is called B perpendicular because it is perpendicular to this plane of arc, and it is called parallel because it is parallel to the plane of arc. Now this B parallel, in case of electric field, these formulas are similar to the electric field formulas. There is only little difference. The formula in this case would look like K I divided by R. In case of electric field, we had K lambda by R, and for B perpendicular, in case of electric field, we had alpha sine square beta cos beta. But in case of magnetic field perpendicular, we will get this alpha will remain same here, but the sine part, beta part will become sine cube beta. This was the formula of E perpendicular, and E parallel was given by k lambda by r, 2 times of sine alpha by 2 into sine cube beta. So this sine cube beta from this parallel goes into this perpendicular, and in case of B parallel, this and this alpha part is for perpendicular and B perpendicular, both are same. Similarly, this part is same for this alpha part is same for both parallel fields, which is ki by r into 2 times of sine alpha by 2, but the beta part is swapped between two. So for this B perpendicular, we take the sine cube beta from this E parallel, and for this B parallel, we will take the value from this E perpendicular, which is this sine square beta cos beta. Only these two values are swapped between this perpendicular and parallel, and the graph of B parallel would be similar to, let's say, the distance from this C point is x of this point P. Then the graph of this B parallel with respect to x would be similar to the graph of E perpendicular, because both have the same relation of beta. So this graph will look like this, where this max value occurs at ry root 2 point. While in case of B perpendicular, the graph will look like this, where magnetic field of this B perpendicular is maximum at the center point. This is x distance. Now next formula, the next formula is for a solenoid. Here in this case, I have wrote a very complicated type of formula. Let's say there is a solenoid, or I should bring in solenoid. If I have any cylinder, let's say this is a solenoid. A solenoid is a long cylindrical shaped body on which wire is wound, and let's say on this cylinder, on this cylinder there is a wire wound like this, and this one loop is called a turn. One loop is called one turn. This one loop is called one turn, and the number of turns per unit length is called turn density. This is called this small n denotes turn density, which is the number of loops per unit length. Let's say at this L length of this coil, there are total n number of turns. So this will give n by L is equal to this n. And let's say the radius of this cylinder is r, and the length of this solenoid is L. Then if this r is very very small than L, then we get one formula for solenoid's field. Let's say there is an axis passing through this center of this cylinder from this point. Let's say there is an axis passing from the center parallel to this like this, and I take any point in this cylinder. There is an axis passing through this, and I take any point P here in this cylinder, and I join the end points of the solenoid. This is a case of finite solenoid. This is not a very infinite solenoid, but a finite solenoid. And let's say this is a perpendicular line drawn from this point P to this line of this this length, and this angle is, let's say, theta 1, and this length is again, let's say, theta 2. Then one more thing we need here is, let's say instead of, in this case of solenoid, when the wire is wounded like in this manner and the current is going in this like this, then we will see that the current is always flowing in this solenoid in a clockwise manner or anti-clockwise manner. At at all points, the current will be either clockwise or anti-clockwise only. So in this case, let's say the current is flowing in this manner in the loops. So current will be flowing in this manner everywhere. And since it doesn't matter if this becomes a complete loop or not, we just what just matter to us is the flow of charge. So let's say if I cut this cylinder and take out a alpha angle part of this cylinder, let's say I cut out a alpha angle part of this cylinder and I remove the rest part of this cylinder, then in that case the solenoid, since this cylinder is cut into some parts, and now the magnetic field at any point P here, due to this left part of the solenoid, will be given as, let's say the current passing is I, then the magnetic field at this point will be given as B is equal to alpha, which is the angle of this cylinder, and K, which is the constant, and I into the turns density bracket sine theta 1 plus sine theta 2. Now if this cylinder is complete, this is the whole cylinder. If I don't take a part of this, but I take a complete cylinder completely wounded like this, then this alpha will become 2 pi, and the K will, if this is a vacuum, then this K will be equal to mu naught upon 4 pi, and this sine theta 1, and if I take this solenoid to be infinite in length, then this value will become sine, this theta 1 will become 90 degree, and this will become 90 degree also. So this will become 2. So in that case, the B will be equal to 2 pi, alpha is 2 pi, K is mu naught upon 4 pi times I into n. This will become 2. So this gets cancelled, and the formula of magnetic fields becomes mu naught In, or we can call it mu Ni. So the formula of solenoid we have learned, which was mu naught Ni, can be derived from this as from this also. Means this case is a simpler case of this, and this is a very precise equation, and that's it. These are sufficient formulas, and there is one more formula for magnetic field I can give. Now as you can see here, all these formulas are written in this, so this is the magnetic field is the straight current carrying wire, and this is for the arc, and this is due to the solenoid. When the solenoid is complete, in that case this alpha becomes 2 pi. This becomes the formula of magnetic field at any point P here. And there is another case of, let's say, a bar magnet or a magnetic dipole moment is given here. Then in that case, the magnetic field can be given at equatorial plane and the point along the axis, just like in case of electric dipole. The formula is just same as in case of electric field. Only the dipole moment vector P is electric dipole moment vector is replaced with magnetic dipole moment. Now the case of magnetic field due to the current flowing in a spiral shape. In case of electric field, there is a point charge which produces field like this. and there is a negative charge, let's say there, in case of dipole moment, and the field goes like this. Sorry, field goes like this in this case. Now in this can be, now this is not possible to get a single magnet, a single pole of a magnet which produces magnetic field totally coming outward, because let's say we have a magnet here, it is north pole here, south pole here, it produces some magnetic field in this direction like this. This is similar to this, but we have some magnetic field going in this direction like this also. Sorry, in this direction like this. Inside the magnet, the magnetic field are in this opposite direction. This forms a complete loop. This forms a loop, but in case of this, there is no loop. The magnetic field is going in this direction and like this. So this is not forming a loop in this case of electric field, but in case of magnetic field, this is forming a loop. And if I cut this magnet into two parts, we will again get two magnets with north and south poles with this same type of magnetic field in the same directions like this, but this will be produce weaker magnets, so we fields will become weaker, but again this will form a loop. So there we will never get north pole separated from the south pole, because every time we cut it we always get a south pole with this north pole. So monopole, this is called monopole, which produces charge, which produces field coming outward only. So monopole is not possible in case of magnetic field. In case of magnetic field, there is always north and south together, which form this loop of field. And but we can assume that there is any kind of monopole in case of magnetic field represented by QM. And let's say there is a bar magnet here. Its moment, magnetic dipole moment, let's say this is M, and let's say its length is L, then this can be represented as L into QM, and the direction is simply as the direction of M. So the dipole moment of this magnet can be written in this form, and this QM will be treated as the magnetic charge. So this concept is basically based on the thing. So this is actually a imaginary concept. This is imaginary. It is just used to tell, let's say, in case of electric field, in case of electric dipole, there is a minus q charge here and q charge here separated by distance L. This produces some field like this. And in case of magnet, let's say this is north and this is south, then it also produces field like this. Both produces similar fields outside, but inside the dipole the field direction in this case reverse, and but in this direction, in this case the field direction is in this way. So it cannot tell the field inside, the inside field we cannot judge, but the outside field, all the fields outside, like in this space and this place, all the fields outside dipole is same for both cases. So here, since these two fields look similar, we can say that this field can be represented by some minus qm and qm dipole, which will produce similar field outside. This is used to tell the field outside only, not inside. So this is an imaginary concept which is inspired by this dipole moment, electric dipole moment, which can help to tell the magnetic field outside in the, let's say, in this plane, in this whole outside region except this inside region. So a dipole moment which, and we can say that if there is a dipole moment of, let's say there is a magnet here, there is a bar magnet here of, let's say, L length, which can be treated like this: L length and minus qm monopole charge here, and minus plus qm positive charge here. Magnetic charge, this is a magnetic charge. We are talking about magnetism. This is imaginary thing, doesn't exist in real. Then it can, then if the point in the space taken, let's say at r distance from the center, and let's say this length is there, and then in that case, if a is very very small than L, sorry, this r, if a is very very small than r, and let's say its length is L, and a is very very small than, let's say, nothing. So let's say this a radius is, let's say this length is L and this radius is a, and here a is very very small than r, and or we can say this would be written more properly written as r minus L comma r plus L. So if a is very very small, then this r minus a and r plus a means this radius of this is this solenoid or whatever this bar magnet is. If the radius of this is very small, or we can say the thickness is very small, then this length, then this length, or let's say this length, then in that case the magnetic field at this point, which is along the axis, Bp can be given as, similarly just like the formula in case of electric dipole, we will say r square minus a square whole square, and the Bp when there is a point in this equatorial plane, let's say here, this is axis on axis outside, and this is on equatorial plane. This is on the equatorial plane, and this won't tell the magnetic field here, this won't tell the magnetic field here, but outside, like this position, this position, and this. So this will tell the magnetic field in these regions, but not in this region. This region inside this dipole also lies in the equatorial plane, but we have to be careful that this is outside dipole. We have to take the point P outside dipole or the bar magnet, and the formula will become k m vector divided by r square plus, so this is this length, let's say this whole length is, let's say this whole length is 2L, then this is right, this whole length is 2L, then the half of this length is L, and we can write it as, okay, let's change some things. Let's write it as 2A q, this is 2A, and let's say this radius is L, and this length is, let's say this length of dipole is 2A, then we are given that L is very very small than r minus a comma r plus a, so it is very very small than both of these values. Now we can write this formula simply as r square plus a square to the power 3 by 2. Formula are same, we must be careful where we have to take the point. Now these are the formulas for magnetic field. And the magnetic moment is given by the formula magnetic moment is equal to a into I, and its direction is in the direction of the area vector. Let's say there is a current flowing in a loop, let's say this is a circle, and current is flowing like this I in this area A. So we will say we will use the right hand rule. Let's say this is current flowing this way, then the thumb points in this direction according to the right hand rule. If I curl along the current, then thumb points in this direction, so that magnetic moment is in this direction. Area vector is taken along this direction where this thumb points. So this is where the direction of magnetic moment is, and the magnitude is equal to area of the loop into the current. Now if I take let's say some n number of turns with I current passing through this wire which are very close to each other, then in that case the magnetic moment due to this coil, due to the coil, magnetic moment of the coil would be even as, since this one, let's say all of them have area A, this is flowing in this direction, so magnetic moments will point in this direction, because if I curl along the current, the thumb points in this direction, so this will become the direction of magnetic moment. And each loop provides AI, each loop provides AI magnetic moments, so multiplying by n we get this much value of magnetic moment. Or I can say that I effective multiplied by the area vector, that is equal to the m of the coil, where I effective would be equal to the I current passes here, here and here. In, let's say there are n number of turns, so the total current passing this whole total number of current, the total current passing would be equal to n times the current passing through one wire which is I, so I can call it as n I into a vector. This would be the formula of magnetic moment. Either I call it I effective, or I simply take it as A effective. It is just my wish. I can take any area vector. I can call it as A effective. I can call A into N as A effective, or I can call A into I into N as I effective. I can write as this or this. The value will remain this. And the magnetic field in the solenoid is given as mu naught Ni. This happens when this happens when there is vacuum. Mu naught is used when there is vacuum. If there is no vacuum but a medium is used, then the formula of magnetic field inside the solenoid at an at the center of the solenoid, which is a very large solenoid, let's say very large solenoid given, then the magnetic field at center along this axis would be this value. And if I bend this whole solenoid to make it toroid, a toroid is like a wire goes like this and coiled around this cell, this ring, then this is called a toroid. And in this case, the magnetic field in this interior, magnetic field inside this tunnel like shape is again equal to this mu Ni. And if this medium is filled with some material of magnetic permeability mu r, then this will become mu r into mu naught Ni. This formula will become this. The medium, the region in which I want to find the magnetic field, let's say I want to find the magnetic field in this region, then I will have to see which material is present in this medium. I have to take the mu r of this material present in the same region in which I want to find the magnetic field. It doesn't matter if there is any material of some mu r to permeability here. If I want to find the magnetic field at this point, then I will have to put the value of permeability here, mu r1, which is the permeability here. Then only then the magnetic field at this point will be given as mu r1 into mu naught ni. And just like in case of torque acting on a electric dipole moment in a uniform electric field, if there is a uniform magnetic field B, then if a magnetic moment, let's say M, is placed in this magnetic field, then the torque acting on the magnetic moment is given by M cross B. This is due to the magnetic field. The torque acting on the magnetic moment due to this magnetic field B is M cross B, and the potential energy equation is given as U is equal to U at any angle theta, where theta is the angle between this M vector and this B vector. Then the potential energy at any angle theta is given as minus M dot B, just like in case of electric field we had formula minus P dot E. And in this case there is a reference taken, that U at 90-degree angle, when this dipole moment is at 90-degree angle with this magnetic field, then this value is taken as 0. Mu at 90 degree is equal to 0. This is the reference, and this is taken as the initial angle. And similarly, if there is in the case of galvanometer, there is a coil of some magnetic momentum, and there is a magnetic field in this medium. There is some magnetic field in this medium B, and the torque acting on this dipole moment would be given by M cross B, which is MB sine theta. And in case of galvanometer, the design of galvanometer is such that the M and B are perpendicular or not. No, they in case of galvanometer, the system is made in such a way that the magnetic field is provided at 90-degree angle to this magnetic field always. This theta is 90-degree always. Then the torque will become MB, and in that case this MB is the force, and there is a, let's say this is a coil here which can rotate like this. This is a plane of coil and rotating. This is a coil and it can rotate like this in the magnetic field, and one end is connected to a spring with spring constant, or we can say tension constant or torsional constant. Let's say this end is connected to some spring with some torsional constant or any material, such that when this object rotates it produces some restoring torque, and the restoring torque in this spring is equal to alpha into some k, where this k is called torsional constant. This is also called tension constant, or this can be called as proportional constant. And in this case, this k is not the k used in the case of magnetic field equation. This is a different k, and we have the, when this and this and this coil is attached with a needle, so that at any equilibrium position, the when this torque becomes equal to this restoring torque, in that case we get some deflection and we get some reading shown in the, let's say there is a coil here and this end of this coil is connected with a needle, and there is some scale here given like this. There is some magnetic field given here, and when some current passes in this coil, this produces some torque in the coil which forces it to rotate with a torque tau, and there is some restoring torque produced as angle increases. Let's say this is 0. angle, when this is some alpha angle produced, when there is some alpha angle produced, then there would be some restoring torque due to this spring attached to it, and this will be, when this will become equal to this r, this will stop at any reading value, and this tells the reading of the current. And this tower can be recorded with, in the equilibrium state, this would be equal to this k, and m is equal to n times I, which is equal to alpha k, and with this multiply by this this value, these two torque values become equal, and this n is the number of turns, I is the current passing through one turn, and A is the area of coil, one turn. So this gives the formula alpha is equal to bi na divided by k, and the value, the all the current per alpha is equal to k, the current per alpha, current taken per alpha is equal to ki over bna. This value is called galvanometer constant. This value k upon bn is called galvanometer constant, or it is called current reduction factor. Now next thing is current sensitivity and voltage sensitivity. The current sensitivity is denoted by Is, which is the deflection produced per unit current in the flowing in the coil, and the voltage sensitivity is given by the deflection produced per unit voltage in the across this coil. So let's say the resistance of the coil is R, and this alpha is given by this equation B I N A divided by I. This gives this is K here, B N A by K. So this is a constant value for any device on any galvanometer and with n number of turns, while this voltage sensitivity will be given by alpha, which is BINA divided by K, and this voltage is equal to I into R. So this would be equal to I into R, which gives BNA divided by KR. So this voltage sensitivity depends on the resistance and number of turns, while and this area, or the mostly varied quantity of this number of turns and resistance. So in this case of current, there is only number of turns, and in this case of voltage sensitivity, there is number of turns and resistance of the coil. So it is not necessary that if Is increases then Bs increases, or if Is decreases then Bs decreases. They can be differently varied also. So this chapter is over for magnetic field. The next chapter is magnetism in matter. So first of all, we have talked about the magnetic field due to the dipole, and a dipole can be assumed to be written as 2a q times m. This is just an imaginary concept. This is an imaginary concept, and the unit of this m is ampere into meter square. Ampere meter square, and this unit is, I guess, called Weber, or maybe something else. There is one quantity called flux, and there is one quantity magnetic moment, and there is one quantity magnetic field. Now let's say there is a charge of magnitude q moving in a, let's say there is a magnetic field in this medium, let's say in this downward direction, the magnetic field is uniform, let's say B, and a charged particle is thrown in this medium with some velocity, let's say V. Then the magnitude of this velocity that is perpendicular to this magnetic field, since the magnetic field is in this direction, the velocity should be pointing in this direction, in this direction, or in this direction, means the velocity should be in this plane. The component of the velocity in this plane will interact with the magnetic field. We say that the force acting on the charged particle, magnetic force on the charged particle, will be equal to Q times V cross B. And V cross B means the component of the velocity V, which is perpendicular to this magnetic field, that is the magnetic field component in this plane. Let's call this perpendicular component as V perpendicular. So let's denote it by V perpendicular, and this will become V. So the force acting on this charge Q by this magnetic field is V. Let's say this is V perpendicular and this is magnetic force B. And let's say there is some velocity of this velocity component of the charge that is parallel to the magnetic field. Let's denote it by V parallel. So the charge has two velocity, one is V perpendicular and one is V parallel. V can be written as V perpendicular square plus V parallel square root. Now we know that when there is this force acting on the charged particle, this force will be acting in the direction V is, let's say the V is in this direction, then V cross B would be in this direction. So the force is always, this force is acting always perpendicular to B. V acts perpendicular to B and perpendicular to B. So the force is perpendicular to these two quantities, perpendicular to this B and perpendicular to this magnetic field. So in that case, we see that the charge will start rotating due to a force acting in this centripetal in this direction. The work done by the magnetic force is zero, because the magnetic force, let's say magnetic force in this direction, sorry, magnetic force is perpendicular to this both magnetic field and this velocity. So we can say that since V parallel is parallel to the magnetic field, V perpendicular is just V perpendicular, and the force acting on the charged particle, magnetic force on the charged particle, is both perpendicular to this B, and V, since it is perpendicular to B, that is perpendicular to this also. So the magnetic force is perpendicular to this both velocity of the charge. So we can say that if the charged particle is moving in any direction, then the force acting on the particle is always perpendicular. Magnetic force acting on a particle is always perpendicular to the velocity. So we can say that FB is perpendicular to the V net. This we can conclude here. This means that work done by the magnetic field is equal to zero on the charged particle. It means that the velocity will not change, the kinetic energy will not change, the time change in kinetic energy will also be zero, because the work done by the magnetic field will also be zero. So in that case, the velocity magnitude will be constant, only the direction of this V perpendicular will change, while this V parallel will remain constant. So the V parallel remains unaffected and V perpendicular keeps on changing. This particle will start rotating, and we know that to find the radius of rotation, there is a centripetal force acting like this. We get, let's say, the mass. We know that the radius of curvature of the path is given by r is equal to v square by a perpendicular. Since the a perpendicular is in this direction and a perpendicular is equal to the total force F, which is perpendicular also, divided by the mass, which is equal to q v perpendicular b, which is the force, divided by the mass of the charge, which is m. This gives the total acceleration of this. So we get v, and this v is the total v square, total velocity a square, divided by this a perpendicular, which is q v perpendicular b, divided by m. And since this object is rotating in this circle with velocity v perpendicular, we will put the value of v perpendicular here. The v parallel, it has nothing to do with this circle. The velocity which is taking part in this circular motion is only v perpendicular. The velocity with which the particle is rotating in this circle is v perpendicular, and this circle is moving in inward or outward direction with the velocity v parallel. This radius of this circle in which this body rotates is given by this, which is equal to v perpendicular m by qb. And the angular velocity of this body can be written as v perpendicular by r, the tangential velocity divided by the radius, which is radius value is given by v perpendicular by m by qb. This omega will be equal to qb by m. So we get one important formula for the angular velocity of the rotation of this charged particle would be equal to qb by m, which is independent of the velocity. And using this equation of omega, we can say that the v perpendicular would be equal to omega into r, and we can say that omega, sorry, right. So the r can be written as omega by v perpendicular, so v perpendicular by omega, which is equal to v perpendicular into m by qb. So we can derive the radius from this equation. So we have to only memorize this equation. Now we can derive all this equation also. And what is pitch? Let's say this particle, there is a magnetic field in this direction, and the particle is moving in this direction with a velocity v initially. Then there would be some perpendicular velocity to this magnetic field in this direction, some parallel in this direction. So perpendicular velocity causes the rotation of this body, charge q, and parallel component causes this circle to move ahead. So after a time t, let's say it started from this point, so after a time t it completes one circle, but this starts look like a helical path because it is also moving forward. So the distance by which it has moved after completing one circle, one loop, then this is called pitch. So the particle has started from this point and it rotates and it is now at this point. Then this length is called pitch, and this pitch can be given by simply the time taken for completing one circle, which is given by time period is equal to 2 pi by omega, and this velocity is v parallel. So pitch would be equal to v parallel into time period, and time period can be given by 2 pi by omega. So this was the case of cyclotron. Cyclotron also works on this principle that the frequency of rotation is independent of the velocity, and the radius is also independent of velocity. It depends on the charge q, b, and mass. So omega is equal to qb by m. This is the important formula here. Now there is one formula for magnetic moment. There is one unit of magnetic moment called Bohr magneton, denoted as Bm. 1 Bohr magneton is equal to 9.27 into 10 to the power minus 24 ampere meter square. So this is the unit of magnetic moment m. in and this one Bohr magneton is equal to this, and one Bohr magneton is defined from, let's say there is an electron revolving in an atom. Then in this case the current due to this electron moving is given as I is equal to E by time period. Let's say this particle passes through this point after every t time, so the charge passing through this point is q after each t time. Sorry, e charge passes through this point after each t time period, so the current would be equal to E by t. And the the orbital magnetic moment, the magnetic moment of this moving charge, magnetic moment due to this moving charge can be given as, let's say this area is a, so the magnetic moment in this case is denoted as mu l. This is the magnetic moment of electron orbiting electron. This is called the orbital magnetic moment. This is called the orbital magnetic moment denoted by the sign mu l, and it is given by the area of this circle in which the electron is orbiting and the current. So area into I. That is a simple definition, and I is equal to E by T, and the area is equal to pi r square. And the formula for radius is, we can put the value of radius as, how can we write the radius? We know that mvr is equal to nh upon 2 pi, and what else do we know? In case of the radius, formula was given by r naught into n, maybe n square. If the formula was, so this value can be written as pi into r square into e. The time period can be written as the total length divided by the velocity. Let's say the particle is moving with a velocity v, and this whole circumference length is 2 pi r, then dividing by the velocity we will get the total time taken to complete one circle. This gives this formula. Then this mu l will become equal to pi, r cancels r, pi cancels pi, we get r v into e divided by 2. This formula of rv can be found from this equation. Rv is equal to nh upon 2 pi m. So substituting the value of this, we get nh upon 2 times 2, which is 4 pi m e by this. Then this is a constant value, this is a constant value, this is also a constant value for this electron. So we can say that for an electron, this constant value, if we calculate it, this comes out to be 9.27 into 10 to the power minus 24, multiplying by this, and this unit is ampere meter square. This is the value of magnetic moment. This is the magnetic moment of an electron orbiting in a radius, in an atom, in any atom. So this value is called one Bohr magneton. That's why the word Bohr comes here. Here we have used the concept given by the Bohr. And that's it. There is one more thing, the mu L divided by L. This is called gyromagnetic ratio. And it is a constant value, where mu L, we know that mu L is given by, this was the formula of mu L, which is given by Rv into E divided by 2, and L is given by mvr. So VR gets cancelled, and this mu L by L becomes E by 2M. So this constant value is called gyromagnetic ratio, the ratio of these two values, just a name, and its value is equal to 8.8 into 10 to the power 10 coulomb per kg. That's it. And there is one thing that I don't know what it means much. The spin magnetic moment of electron is same as the numerical value of 1 Bohr magneton. That is the 1 Bohr magneton is equal to this. Then the spin magnetic moment of an electron is equal to this value. So now talking about the magnetization. So the magnetic field, let's say there is a device here which produces some magnetic field here called B naught. The magnetic field due to this device at this point would be, let's say, mu naught. I am not considering any medium here. If there is no only vacuum air, if there is only vacuum air, then this source produces B naught magnetic field air, and this B naught magnetic field can be written as mu naught into H, where H is can be written as H is equal to B vector upon mu naught. This one quantity is very useful, and now let's say I introduce a medium in this case here of permeability mu r. Relative permeability of this medium is mu r. In this medium there is a point P here again. Now the magnetic field due to this coil will remain same B naught, but this medium also produces some magnetic field in the same direction of this magnetic field. For example, let's say that's the direction of magnetic field depends on the relative permeability of this material. It can have negative permeability, it means it can cause the magnetic field to act in the opposite direction, and or it can produce some magnetic the medium can produce some magnetic field, let's denoted by Bm. Then this Bm can be in the opposite direction of B naught or in the same direction of B naught. It depends on the value of mu r, where mu r can be negative, 0, or positive. So in this case, the mu r is never negative. Mu r is never negative. Mu r is always greater than 0. Greater than 1. Right or not? Or 0, maybe. Okay, I have to check it once. Just 1 minute. Since mu r is equal to the magnetic susceptibility plus 1, since it can become -1, so we can say that, okay, mu r is always greater than or equal to 0. It is never negative, and the value of this magnetic field depends on the Chi, magnetic susceptibility of the medium, where this magnetic susceptibility can be negative, 0, or positive. Can be magnetic susceptibility file, by the way, is never 0. It is generally negative or small value in positive or very large value in positive. And let's say the magnetic field due to this medium would be written as this H multiplied by this Z. So this value tells the magnetic field produced by the medium, and this tells the magnetic field produced by the system, and the total magnetic field at this point would be equal to B net is equal to B naught plus PM, which is simply H bracket, sorry, H mu naught bracket 1 plus xi, where this value is called mu r and this is called, this whole value is called mu theta. Now this net magnetic field can be written like this, where is mu is the magnetic permeability of this medium. And there is one more thing here. In case of electric field, we saw that electric field has same dimension as the dimension of sigma over epsilon. Similarly, in case of magnetic field, this will have same dimension as sigma. This is the charge. This was the charge density. Sorry. This had the dimension of, let's say, P, the magnetic moment. The polarization in case of electric field was defined by P net dipole moment per unit volume, that net dipole moment divided by the volume in which this dipole moment is present. Similarly, in case of magnetism, there is magnetization, it is called polarization in case of electric field, and in case of magnetic field it is called magnetization. This is equal to the magnetic moment net divided by the volume, and this value can be written as xi into h. This magnetization is equal to xi into h. So it depends on the source field. The source field which is making some field here. The magnetization of this medium depends on the source which is producing some field here, and this magnetization is equal to xi h. So this is one important equation. This is second. And the ferromagnetic phenomena is caused because, let's say, there is a material here. In case of ferromagnetic materials, there are some crystals in these materials which are called codomains. These domains are like small magnetic. These domains in this medium are like small magnets. These are like small magnets in this medium, and when we provide some magnetic field, and if I provide a strong magnetic field, all these magnetic fields start aligning in a direction. All these magnetic moments are start aligning in a direction of along this magnetic field direction, and since they are not easy to move in this medium, if I remove this magnetic field, even after I remove this magnetic field, this will retain its magnetic field. These domains, these small domains which have these magnetic fields, small magnetic fields, they will retain their magnetic field direction. So if I remove all the sources, they will retain this magnetic field. So let's say I start with a material which is not a magnet right now. Let's say there is a iron which is not magnetic now. In this medium, there are some atoms which have some magnetic fields in the random direction. They make groups, they make small groups together. These atoms make a small groups together. These small groups are called domain, and all these domains have a magnetic field of their small magnetic field of them, and a small magnetic moment also. Now what happens, these will be pointing in random directions. These magnetic moments would be in the random directions, and if I provide some strong magnetic field in this medium in a direction, all these magnetic moments will start rotating. All these behave like a small magnet, and when I provide a magnetic field, this start rotating, and they will start aligning themselves along with this field. And then after some time they will be aligned in this direction. And now this whole iron has become magnetic. Now if I remove this external magnetic field, this will persist, this will still retain its magnetic field's direction, the domains will still hold its directions. And now there is a net magnetic moment pointing in a direction which causes some magnetic field in this iron. Initially there was a random initially these magnetic moments were pointing in the random direction, but after I applied the magnetic field, these started pointing in some specific directions. So that's why, and since these cannot move easily, this cannot change direction easily, they start it now starts behaving like a magnet, because there is a net magnetic moment in a direction. But if I heat it, if I provide some heat to this iron, it will increase the thermal energy of this small domains, and this will increase the thermal energy, and now this can easily move in this medium. And as it starts moving in this medium, this will start pointing into the random directions again, and after heating, this iron will lose its magnetic property. So that is why the heating of any iron or any substance makes it lose its magnetic field or makes it weaker. In case of paramagnetic material, the phenomena is caused on atomic levels only. There are some atoms and the electrons, the atoms don't form clusters of. In this case of paramagnetic materials, there are no domains. There are no domains like in case of ferromagnet, but the magnetic field when provided, external magnetic field when provided, these electrons start aligning themselves in such a way that they point in the direction of the magnetic field. And after I remove this magnetic field, they become normal again. So these become magnetic only when the magnetic field is applied, because the electrons start arranging themselves. In case of diamagnetic material, the electrons motion in this medium is in some opposite ways, such that it produces opposite magnetic field. And after I remove the external magnetic field, this effect is gone again. In these two cases, the phenomena is caused at only atomic level only. The electrons orbit is affected due to this magnetic field provided. In case of ferromagnet, the domains start pointing in a specific direction, giving a net magnetic moment. There are some example of diamagnetic material, which is like some conducting materials, some important materials like diamond, copper, and then lead, silicon, bismuth, and nitrogen. These are diamagnetic material. And paramagnetic, this includes aluminum, chromium, lithium, magnesium, oxygen, platinum, and tungsten. These types of material are paramagnetic in nature. Ferromagnet is, let's say, alnico, nickel, co- cobalt, iron, and gadolinium. These are ferromagnetic materials. Now this chapter is over. That's it. And the xi is equal to xi plus 1 is equal to mu r. Mu r is always, according to this will always be greater or equal to 0, because minus 1 plus 1 becomes 0.